So today's talk is going to be given by Michał, who's a PhD student in Warsaw. His advisor is Marek Cygan, and his main work is on online. Well, it's very wide. It ranges from online algorithms, as presented here, approximation algorithms, and also things like hardness and B.
Okay, so this is Halloween talk. So I'm sorry I don't have costume, but I put some bats on slides. So this is a joint work with Stefano, who visited us last week, and also Fabrizio Grandoni and Marek Adamczyk. And I'll start with what is universal optimization about. Introduce some new benchmark, and then I'll give some deeper detail of some of our results. So universal algorithm is about pre-computing reaction for scenarios that are not known in advance. So, for example, for set cover, we can think about each element as a client, and the set covering procedure as kind of service. And each client wants to be covered, but we don't know which clients are going to be active. And for each client, we want to choose one of the sets that covers it. And for example, here I put colors to the elements. So this is an example of such an assignment. And afterwards, after this assignment is done, the set of active elements is revealed, and we then need to pick all the sets that were assigned to them. And another example can be directed Steiner tree. And here each terminal needs to have a path to the root assigned in advance. So these are 3 terminals with their paths, and then these 2 are revealed to be the active ones. And this is the solution they induce. As can we see, this solution is far from being optimal, and this is like because we cannot like foresee what exactly we are going to cover.
So this is like a non-adaptive online. I mean, it's non-adaptive solution for an online algorithm, right?
Like online is too big word, because there is only like one moment of revealing the
input. Well,
the input. Yeah. So this.
But you can okay. So maybe you're saying that this is just a 2-step thing, but this could be like a
non-adaptive online algorithm. Yeah.
Also can be viewed this way. Okay.
Mm-hmm. And people were interested in competitive ratio of such an algorithms. So like, how bad can be the solution we offer to the active set with comparison to the optimal solution. And it turns out that it can be actually quite bad, even for universal vertex cover. So in this setting, like we want to cover each edge with one of its ends, and this is equivalent to choosing a direction of each edge. And for example, for let's say we have this assignment made, and this is some subset revealed, and the optimal solution is to cover these edges only with the one purple node. But our assignment would choose all 3 of them. And there is an easy argument that there is some vertex with big out degree, so there will be one scenario in which this ratio would be really bad.
How many scenarios do you have? Like, do you put a constraint on the number of scenarios here, or for general?
So it's like in set cover. So the number of number of scenarios.
For universal set cover or universal vertex cover, you have this question of different scenarios can show up, and these are explicitly given scenarios.
So we consider three models. A scenario model where we have list of all scenarios, and this is part of the input.
And like this one, for this, what you're saying here?
Yeah, here they are given as a list because there are like the number of scenarios is the number of vertices. Yeah, in this example.
Like you said, one vertex. Each scenario is one vertex.
Yeah, each scenario is one subset of vertices, right?
One subset of vertices.
In this example, each scenario is a subset of edges to be covered, and each such subset can be associated in one vertex in this special instance.
So each scenario is all edges connected to one vertex. You have number of vertices.
That's right.
So the optimum solution in each scenario is one.
Yes.
No matter like if you have high degree,
Yeah, and for every assignment we can find a vertex where this assignment would provide a bad solution. So I'll
like in general
that lower bound there, omega max m comma root n is for what model?
This is for scenario model, and this also applies to oracle model, which is more difficult. But I want to talk about these models of scenarios later.
Okay, but when you say scenario model, the number of scenarios is polynomial in M and N.
Yes.
Right.
Yes. Or it's a part of the input, so we don't want it to be large. Okay, so this is like main message is that the competitive analysis for universal algorithm has big lower bounds. And some idea is to make adversary a little weaker. So one might consider a model where this scenario is drawn with a probability distribution that the algorithm knows in advance, and we want to minimize the estimated cost of such a solution. And here, if we analyze the previous example more carefully, you can see that you could still get this square root of n lower bound also in this model.
But you want to minimize the expected cost, right?
Yes.
Okay.
And some idea is to consider some limited family of probability distributions. For example, we can say that each element is being activated independently, and for such a model, Fabrizio et al. Proposed algorithm with a competitive ratio logarithmic in M, where M is the number of sets, and the M might be exponential with respect to n. So this is still far worse than for the classical set cover, and like this competitive ratio is tight. So what we try to do is to replace this competitive benchmark with something more fair. So in competitive analysis, we are comparing a single algorithm with expected value of the optimal solution. But this is not given by any algorithm. This is just optimal solution given by some oracle. And what we propose is to rather compare against some best assignment, best algorithm that plays by the same rules as we do. And one can think is that this competitive analysis is like comparing apple to oranges, because there are different classes of solutions being compared. And we claim that this is a reason why these lower bounds are so huge.
So go back. That's very interesting. It's like it goes back to questions for 15 years. So like this second model only makes sense if you have IID, like a known distribution stochastic model. It does not make sense to define this new thing in a model that you don't know the distributions in advance.
That's right, because
because like the definition of the space of solutions become.
We can also compute something like worst case ratio.
Like unknown distribution. Okay, so like you have to specify what you mean by these solutions, that the apples. Okay, go on.
Wow, this comparison can be made at several levels, right? The first one is handicapping because the optimal is instance-specific benchmark.
Yeah.
You are a single algorithm. If you want to do distributions, you could do another thing. This is you're saying both the algorithm and the benchmark are distribution-specific.
Yeah.
One slightly better apples versus oranges comparison in between is algorithm is distribution agnostic. It is drawn from some bag of distributions you don't know, whereas the benchmark is distribution specific. But it is not instance specific, because the first one is instance specific. So that is another
distributions. But you will tell us what you mean by this. So we still have this question of. Okay.
So one example of results in this apple to apples benchmark is a result by Carver and Minkoff that show that Steiner tree admits constant approximation in this approximation benchmark in the independent activation model. So each terminal is activated independently, and we need to connect them to the root.
No, like this result is in this model?
Yes.
So the benchmark that they compare with is the optimum dynamic program type solution for this independent activation model, where you know the distribution in advance. Like we know in advance what is the probability that each client is activated.
Yes, they call it maybe cast problem, and they put it in some in different words, but this is totally equivalent to this analysis.
That's interesting. I never thought of that.
Okay, so I'm going to say like how to approach to set cover, which will be the simplest algorithm of our toolbox. So this is a classical LT formulation for set cover, and we replace this variables xs with configurations. So what changes? Like now we cannot have one variable for a set, because the cost of taking set depends of how many elements would be covered, but would be assigned to it. So in the objective function, we get this probabilistic term, and so this is the probability that at least one of the assigned elements would be active.
So are you in like the previous language? This is a scenario based universal set
And
cover model.
now I'm talking like model oblivious. Like we are given a probabilistic distribution, and we can like let's just assume we can evaluate.
Okay.
Something like that, and then I will talk more about specific models.
So B is the set of it's a set of what?
Elements that are going that are assigned to S. So if we have integral solution, then setting this variable to 1 means that all elements from B are assigned to S and only them.
Oh, and wait, but this is like summing over all subsets, right?
Yes. Yes. So now we have exponential number of variables. This is configurational LP. So, like with comparison to the previous one, we can see that the objective function like changes because this new term and the rest is more or less the same. So there's a exponential number of variables. So in order to solve such an LP, we need to go to the dual. And in dual LP, we have now a polynomial number of variables and exponential number of constraints. And if we are able to provide it with a separation oracle, then we could solve it. So for each solution vector, we need to be able to check if it's a feasible solution. And if we can check something like that in polynomial time, then we could solve the dual, and with some known tricks, we can also solve the primal LP. So the main observation here is that this activation function is submodular because like it's a combination of very simple functions for like a sum of functions for each scenario. And when we take sum of submodular function with positive coefficients, this is also submodular.
So this is independent activation? Or this is general?
General.
Okay.
So what is crucial about submodular function is that we can minimize them in polynomial time.
So P is not a family of subsets. It's a subset of elements. Confused.
What is confusing?
So the scenario, the set cover scenario, I'm trying to reverse engineer what is the problem that you're trying to solve. Why are you writing this NLP?
Mm-hmm.
Is it that, so like this, what is the problem that you're trying to solve? Universal stochastic set cover? Is it you have different scenario, each scenario corresponds to a family of subsets? Or each scenario corresponds to?
So I don't have this on any slide. But I believe there's nobody GVCing, so I can
there
just.
There is one person.
No, there he dropped out.
He dropped out. There is nobody.
Okay. So what we are trying to minimize? We are given our universe. Universe of size n and the family of sets of size m, and probabilistic distribution, which is over
elements or sets?
sets.
Subsets of elements or something.
Yes, so
Subsets of elements. So these are the
Like
these are
subsets of
the these are the. Is it like a probability over elements or sets? So like
sets.
No, it's a probability distribution over scenarios. So each scenario is a set, right? He has m scenarios.
No,
each
those
scenario
are.
is a subset of elements.
Each scenario is a subset of elements.
So they're subsets of view, right?
So each scenario is a subset of elements.
Each scenario is a subset of elements.
So like these
and
are
then
the
you have-
elements at your disposal to cover all the sets that you have to cover. Or no, these are the elements that you have to cover. This the subset of the family of subsets that you have is fixed. In each
Yes.
scenario, you have the same
Yes.
family. It's just the
Maybe
so
I
that's
just
one
go
source
back to
of
the
confusion.
first slide and
The scenario is just to
example.
capture inputs, right? The input is captured by scenarios, and there are case scenarios. There is a
Scenario is
probability distribution over scenarios. The probability distribution could be a generic probability distribution or independent probability distribution. That's all.
Okay.
What he meant by scenario independent LP is he doesn't say whether it is independent or not.
So each scenario is a subset of elements that you have to cover.
Yes.
And the sets that you have to cover them with are fixed. In each scenario, it doesn't matter.
So to make everything clear, let's go once again through this example. So now the elements that are not gray is a scenario that was revealed. So this is subsets of elements that we need to cover, and these three sets that we can use are fixed and no from the beginning. And so like we have this assignment here, and after this scenario is revealed, then it induces a family of sets that we need to pay for.
So U is the elements and S is the what is S? S is the
Family of sets. So
but this is not a scenario. It's what you can use to cover, right? S.
yes.
Okay.
Like in
Okay, it's just I think it's a bit. I think what's confusing me is that S is not scenario.
Yeah. S is fixed.
Okay, S is fixed. Okay, I see. And then the probability on. Okay.
yeah, and the distribution is also over the family of
Yeah.
subsets, and what we are minimizing is expected value, and this is X drawn from the pi distribution, and this is sum over all sets that are in a image of X, and this is cost of this set.
Oh wait, what is it? X is the. What is the image?
No, before even any scenario is revealed, you are supposed to say for each element which set you are going to use to cover.
This is what this is the solution.
This is a solution.
Okay.
Yes.
This is solution mapping from elements to sets.
But then I don't think it's you don't do it with multiplicity, right? So it's
here no like
okay.
You have to have an independent set that, but then when the scenario shows up, you look at each element, you pick the set that was supposed to choose as cover that element, and then the cost of that solution is the ones that you have to pick from your predefined solution.
Yes.
So the more overlap you have in that choice, the better. But yeah.
Okay, so are we now on the same page with?
Yeah.
So what can the optimal algorithm do that like isn't captured by this?
The optimal is because the benchmark that you had, right, is instance specific optimal. That means you do it after the scenario is revealed,
But
or you do it before the scenario is revealed. That's the two kinds of benchmarks, right?
What's the new benchmark?
So
Okay,
the new benchmark is the best mapping. So this is mapping minimizing this quantity.
Okay, and then you compare what you can do in polynomial time to this.
the mapping that has the best expected cost.
Okay.
Yes.
Makes sense.
Okay.
Fair enough.
So when this is settled, we can go back.
So now go to the Karger-Minkov. Go back. This is a nice theorem, but I think for stochastic Steiner tree, I was under the impression in the independent activation model, you can even compete with the harder. Is it true that you can compete with this harder thing? Like there's a Stefano Leonardi's paper that does that. So this is a weaker result compared to that. It's like more recent. Or am I wrong?
I can't say if you can get constant competitive ratio for Steiner tree. I don't remember.
Okay, I'll tell you. I'll show you the paper I saw, and like we can discuss. Go ahead, go.
So you're saying you can compare against instance-specific optimal if you relax the set
For
of
the
probability
Steiner tree.
distributions.
That's for Steiner tree. That's Anupam, Stefano.
Okay, so are we now?
Okay, now B is subset.
Do we know how this corresponds to the problem? So like we encode this assignment phi, this mapping using variables y. In the same manner as in the classical set cover, but we need to take into account this probabilistic term.
But does it mean S has been chosen by all elements of B or some element of B?
If we consider optimal integral solution, then it's only like it's exact.
Exactly.
Subset.
Okay, I see.
Yeah, but when we do like linear relaxation, that of course like we can allow these variables to
Sure.
to be like more to be less strict. But in optimal integral solution, yes. So coming back. When we go to
So in the optimal integral solution, like every element in P chose S.
And none outside.
So in order to solve the dual LP, we need to provide it with separation oracle. So for the vector of alphas, we need to check if all these inequalities hold. And the number of inequalities is exponential because there is a quantificator of all subsets B of S. But since this function G that defined as follows is submodular, then this function at the bottom is also submodular.
That function is submodular not under only like independent cascade activation model or something.
It is always.
And it comes from so why that function submodular is you have to derive it and then observe it. No, it's not immediate.
It's quite immediate.
Okay, so then I'm missing something.
So this
the product of no, it's not for the independent model. So you see why that function is submodular?
I think he's going to write expand
the sum over all subsets. Take a probability of this subset being drawn, and here this is like 1 if this is non-empty, and 0 if it's empty. Okay? And this function, as a function of B, is submodular. This is...
It's basically the membership.
Yes.
Yes, hardware that or not.
Yeah. And we take combination.
Combination of that. Okay, makes sense.
When we add additive term, we still have submodular function, and in the oracle, in the separation oracle, we just need to minimize such expression for each S from a covering family. So we can solve this LP in polynomial time, and the rounding procedure is the same as for the classical set cover. So we can round it with the logarithmic waste. So concerning...
Are you trying to tell us an algorithm now? Like this was an algorithm that you described.
Yes.
For set cover. You're describing an algorithm to solve this universal stochastic set cover.
But this is like this is the whole algorithm for set cover, for universal stochastic set cover. And concerning the model, we need to be able to evaluate this function G, and this is trivial in scenario model because we iterate through all scenarios and we check how many overlap with a given set B, and in the independent activation we have formula for that. For the oracle model, so a model where the scenarios are taken from a black box, and the algorithm can just sample oracle a few times, and judging on the results can make decisions. We can reduce it to scenario model in pseudo-polynomial time. So where for unweighted instances we get polynomial time, but for weighted instances we can show also a lower bound of square root of n, and the idea is that if the weights we can hide a relevant part of the input with a really low probability, and this gets as hard as the pure universal optimization, because the algorithm cannot learn anything about the distribution on the relevant part. So how are we with time? 20 minutes. Okay. So now, because this was the simplest algorithm from our paper, and now I want to show something more sophisticated. And here I will show how to use the assumption, how to use the independent activation model. So consider a facility location problem. So we need to assign clients to facilities, and we need to pay for opening each facility and pay for a distance between the client and its facility. And this is the definition of the classical problem without any stochastic stuff. And there is nice constant factor approximation, but only when the function d is given by a metric. Because if it's non-metric, one can reduce set cover. into facility location, and then one needs one can get only logarithmic factor. And when we go to the stochastic, universal stochastic setting, we are looking for the again like best assignment, but we pay for like opening a facility only when there is like only at least one client active who wants to use this facility. And the costs of like transport are additive. Wahab, are you with us?
Yeah.
Okay. So this is like a very similar LP formulation to the previous one, but now there is this additional additive term on the right. And we can also solve it, but we don't know how to round it to get a constant factor approximation in the scenario model. But in the independent activation model, we have this nice inequality because we can express this function g. So this is the evaluation, the activation function of a set. We can compare it with almost linear function. And this is also a trick that Karger used in the work on Steiner tree. So when we replace this g of b with this almost linear term, we would lose only constant factor. So let's do that. And I only replaced g of b with this term. And now this is like almost linear program. And this is, and one can interpret this LP as a rent or buy problem, because when we take a minimum of 1 and sum of probabilities, one can interpret this that you can pay 1 and like open some facility for everybody, or every client can pay independently when he wants to use it. And using this rent or buy interpretation, we can reformulate this LP into equivalent one. So now this variable x stands like the purple variable stands for clients contributing to opening the facility for everybody, and the blue variables that are clients that contribute to, they pay for opening the facility only for themselves. And now it's a purely polynomial LP, and we can just solve it. And in order to round it, we consider we split clients into two groups. The ones that prefer renting or buying. So when we look at only the big clients, so the ones that have the purple variables summing to at least 0.75, then the middle term of the objective function vanishes. And when this happens, when we keep only the purple variables, this is just a classical facility location, but with this additional term GC next to the distance. So this is a facility location in a distorted metric, and this can be solved via primal dual scheme. with factor 3 approximation. And when we consider the small clients, so we consider only the blue variables right now, then this LP gets trivial because like there are no dependencies between clients, and for each client we can buy the facility that is cheapest for him. We need to rescale these variables in both variants, and this is why we chose that this constants, and so there is 4 factor rounding scheme for this LP, and since we use this trick that replaced G of B with this almost linear term, we also lose another factor, and this is in the end we obtain something around 6 approximation.
Why is it 4? Doesn't follow, bro.
Okay, so for the big clients, their constraints are only satisfied up to 0.75. So we need to rescale these variables.
But couldn't you change the threshold of 3/4 and 1/4 to play with the? I mean, I think I'm asking, why is this division into more than 3/4, more than 1/4 optimal?
Because of the rescaling procedure. These purple variables for big clients, they form a feasible solution for facility location in a distorted metric, but after rescaling times 4 by 3. Yeah, and again, and we also lose this factor 3 on them, so this is 4 on total, and we need to rescale the small clients times 4, so this is the optimal threshold. Okay, so this was the sketch for the facility location, and this is the overview of what we are able to obtain. So for the set cover, we can also adapt a greedy algorithm. So we then get a deterministic algorithm with just n harmonic number ratio, and it works also for constraint set multi-cover. So set cover with when each element might request to be covered multiple times. So for vertex cover and edge cover, we also are able to provide the same approximation ratios as in the classical setting. And also for the directed Steiner tree, we are able to adapt the easiest approximation algorithm, because there is a approximation, kind of approximation scheme for the directed Steiner tree, and we are only able to adapt the first level of this scheme. And in the independent activation model, we have this constant approximation for facility location that I just showed, and in the similar framework, we can also handle multicut. We have this lower bounds for Oracle model. And the most interesting question is getting general algorithms. So without this assumption of independent activation for the rest of problems. So facility location, multicut, and Steiner tree. From multicut, the best what we can hope is logarithmic approximation, and we will also want to have it in a scenario model. So that's it.